Thank you. It's an honor for me to be here. So my name is Dieter. I'm originally from the small but beautiful city of Ghent in Belgium. But I did move to New York recently to work at Vimeo. And Vimeo is a video sharing platform. And at Vimeo, I focus on two things. Making sure that our video transcode clusters and our storage clusters are functioning properly. And I also do a lot of time series metrics processing, like graphite stuff. And one way where those two come nicely together is our upload routing. So whenever you go to vimeo.com/upload, in the background, it actually checks which are the closest data centers to you, and then it compares those data centers using a bunch of criteria like disk space, transcode job, wait times, performance of our clusters, and stuff like that. And then based on that, it actually automatically makes a decision which data center to route your upload to. So we not only use graphite to visualize and alert on metrics, but also as a feedback loop for automatic algorithms. But that's actually not what I'm going to talk about right now. I want to talk about some problems that I've seen with metrics, and then what Metrics 2.0 is and how it addresses those problems, and some implementations and examples. So I'm going to be talking mostly about stuff that applies to graphite, although I've tried to keep it as general as possible. So let's start with the terminology thing. This is the terminology that I've seen other people use the most. And basically, they say, OK, a time series is your sequence of data points. You have a timestamp and a metric value per data point. And the metric is a piece of information that refers to the time series. So the metric is nothing more than, for example, a string in graphite, or in some other systems, it's a string and a few tags. And the problem that I have with this, if I have an information need, like how many page requests per second is Vimeo doing, or what is the write performance of a given server, and I need to find these metrics, I need to start browsing in hierarchies. If I'm lucky, my dashboard has a search feature, but it's hard to know which keywords to search for. Maybe I have to start searching in source code or in documentation, ask people. It's very time consuming. And then once I actually find some metrics that seem like good candidates, it's hard to understand what they actually really mean and what the difference is between those metrics, what unit they're in, and where and how they're being generated, which is especially hard because often the name is dynamically generated at runtime. And they often use prefixes that are unclear what they mean or what they're for. Another example is a collectD metric. It does something with timings for writes to disk, but what terminology is being used and which field goes where. Is this the total so far, or does it start from 0 at every data point? Is it an aggregate? What kind of aggregate? And if you have a data point at timestamp X, does it actually refer to the time frame just before that or after that? And also, what if I want to change the agent and keep the same information but just running in a different agent? Does that mean I have to change all my graphs because the metric identifiers change? So there's a lot of unclear and inconsistent terminologies and formats. Metrics are tightly coupled to their sources, and they often lack a lot of information. I would even say that for every source code base that is emitting metrics, and for every person involved working on these metrics, and for every aggregator processing your metrics, the combination of all of those, there's just so many different terminologies and formats. Oops. Even worse, one metric name can have multiple meanings. For example, in collectD, there's an option store rates, and it actually changes the data that is being stored. But it's not reflected in the metric. So by just looking at the metric identifier, you don't know anymore what it actually means. So there's this problem that from an information need, finding the right metrics is hard. And for given metrics, actually understanding what they mean is hard too. So it's a vicious circle. And it gets even worse when you realize that on a lot of graphs, you actually need multiple metrics and multiple kinds of metrics. So I would say that composing graph definitions, whether you do it through a nice UI or by typing text, is redundant. Also because you have to always type the title, you have to say what's in the legend, what should go on the y-axis. And you have to do this explicitly, even though the information could be implicit from the metric names. So it's time consuming, and it's also time consuming because of another reason that I forgot. Oh yeah, because sometimes like you want to represent the same information but in different perspectives, like the same metrics but just in a different graph, and you have to redefine those graphs, and it's so annoying. And then another problem, With a tree model like that Graphite uses, if you have metrics that are in different subtrees, for example, a metric, you want to correlate a metric from an application that you wrote with a metric from one of your metric collection agents, they have different prefixes, they're in a different subtree, and often they're being segregated by different dimensions. So it can be really cumbersome to try to correlate them or aggregate them together, stuff like that. And of course, the more metrics you have, the more this becomes a real problem. So Metrics 2.0 is a concept that tries to solve these problems. And it's about self-describing metrics, metrics that are standardized and that use orthogonal dimensions for all your pieces of information. And I'll show you how that looks like. So this is a typical metric, the way it looks like in Graphite. This is actually a metric coming from Swift, which is comparable to S3. But OpenStack Swift, you can run it on your own hardware. It's open source. And in Metrics 2.0 format, it looks more like this. So all the dimensions are orthogonal to each other. You can correlate or aggregate on any dimension that you want. They are independent from each other. It's standardized because there are specifications that tell you which keys and values you should use to represent which things. And in specific, there's the unit tag, which is mandatory. And also, the design goal is for this to be self-describing. Like, you should be able to know everything, what this means by just looking at it. Also, it's about allowing a few more characters, like a slash, which can be useful in unit tags. Dots can be useful for host names. And also, it allows you to specify extra information that doesn't change the metric identity. Because with a system like Graphite, if you add information, that actually means a new metric identifier and a new time series. But it can be very useful to specify extra information and even change that information later on without changing the actual time series. And for example, one way that this is useful is to track where a metric is coming from, which file and which line number, so that in case you get a massive influx of metrics or if you get invalid packets or anything like that, you can track it down easily. And it's important to realize that this is just a conceptual model. And the wire protocol, you can still use a simple line-based protocol. Actually, we have a protocol that's backwards compatible with Carbon. And also in the storage, you can still use an integer or a string key or anything like that. In fact, it's pretty easy to convert the structured representation into a serialized string and vice versa. So on the website, you can find the concepts explained in detail and the specification and stuff like that. But in particular, I just want to point out the unit specification. So we start out with the SI and IC standard. That's a very common scientific standard. And then on top of that, we just add metrics that are very common in our field, like bytes, errors, warnings, jobs, files, requests. And you can also define compound metrics like megabytes a second, errors per day, requests an hour, stuff like that. So, and the main advantage of this is that you understand immediately what a metric means or is supposed to mean. And you can minimize your time to graphs, and I'll show this later. You can minimize the time it takes to come up with alerting rules and to debug issues. And compatibility between your tools improves a lot, and you're more flexible in choosing your tools. So let's start with some implementations and examples. So let's say you want to get a metric in this format. If you already have a lot of metrics in your Graphite system, then you can use this library called Structured Metrics. It comes with Graph Explorer, which is a dashboard I'll talk about next. And basically, you just define plugins with regular expressions that parse out metrics. And like that, you can add tags. And this is basically all it takes. It comes with plugins for Carbon, StatsD, OpenStack Swift, Diamond, and CollectD. But you can easily add more to it. If, however, you have the liberty to add more metrics, to add new metrics to the system, then you can do it natively. So in this protocol, which is like the Carbon protocol, the first one is one that we're used to. The second one is in the 2.0 format. A Carbon tagger is just a service that sits in your pipeline, and whenever it recognizes a 2.0 metric, it just updates the database. So this is how it looks like. Your metrics flow in, Carbon tagger parses out all the ones that it recognizes as 2.0, stores it in the Elasticsearch database. Your metrics go in Graphite, and using the structured metrics library, in a cron tab or something, every once in a while, you just go over all your metrics in Graphite and you upgrade them to 2.0 format. It is important to realize that the Elasticsearch database just contains the metrics, so the identifier and the tags. It doesn't actually contain the time series data points. That's still in Graphite. And then there's this other service, statsdaemon, which is very similar to Etsy statsd. It's basically drop-in compatible, but when it detects that a metric is in 2.0 format, and for example, when you have incoming metrics in unit and bytes, when it converts that into a rate per second, it will actually update the unit tag. Or when a timing metric comes in milliseconds, it still does all the same summary statistics as you're used to, but now it expresses that with a stat key. So, and the idea is that your metric is always in sync with the data. Okay, so Graph Explorer is the dashboard where everything comes together. It's like, you know, the prototypical implementation of what all those things you can do with Metrics 2.0. So, and by default, the interface you get is just a simple query input. And a query can be just words and patterns that you know are going to match parts of your metric, whether it's the metric identifier from Graphite or some of the keys and values of your tags. So in this case, oh, and you can also specify conditions on your tags. So in this case, we're querying for all the metrics that have something to do with Swift, proxy server, coming from servers matching a certain regular expression, and that have a unit expressed in milliseconds. So that gives us this interface. And Graph Explorer, after executing your query, it shows you first that explanation section where it tells you everything it did and what's going on. And then beneath that are all your actual graphs. And one thing you'll notice is that we display a lot of tags all over the interface, but we only display the tag values, not the keys to save space. But all the tags are color-coded. So there's a tag legend up there, and basically that tells you all the unit tags will have their value displayed in yellow, all the target type, which is like a counter, gauge, and so on. Those values will be displayed in green. And so the important thing to realize is, okay, Graphite queries all the metrics, it collects them, but then it groups them into different graphs. And how it does that is by looking at the group by clause. And by default, it looks at unit, target type, and server, meaning that all the metrics that have the same value for unit, target type, and server go on the same graph. So in this case, all the metrics on this graph are in milliseconds, are a gauge, and come from our proxy 1 server. And then, more in general, all the tags on the left side, on the y-axis, and in the title, those are all the tags that the metrics on this graph have in common. Whereas the tags on the right, in the legend, those are the tags that set the metrics apart from each other. So, at this point, you can start to understand like the metrics you're getting and how you can actually make this more representable, how to make this more useful. So for example, let's say we're going to narrow this down by adding the word upper 90 to get all the upper 90 percentiles. We're also going to select a certain time range from and to a time specification, which is comparable to what Graphite does. And let's say we just want to smooth out the graph a little bit. We're going to say average over 5M, meaning average it over 5 minutes. But there's a lot of other things you can do with that. And then let's say, okay, I want to know how puts and gets compare. I want to see that on a stacked graph. So we add stack, and then we say HTTP method has to match either put or get. Swift type must equals object. And then average by HTTP code and server, because we don't care about those dimensions. So that's how it looks like. We get our graph. It's showing puts and gets, averaged across all different values of server and all different values of HTTP code, because we don't care about that. And it's basically telling us puts are slower than gets. Another example is, let's say we want to see how servers compare. The main difference here is that we're going to say, okay, group by unit and target type, not by server, so that different values of server go on the same graph. And then just average over all the other dimensions, because we don't care about them. And then you get this kind of graph. And it's basically telling us that one of the servers is much slower than all the other ones. And it's showing us all the 4 servers averaged across all the other dimensions. Another example, let's say I want to get more insights into our transcode jobs that are running. So I just type transcode and unit equals jobs per second. That basically gives me this overview. As you can see, there's a lot of time series there, mostly because there's a bunch of different job states, like active, starting, failed. And also there's a lot of different zones. You can see the zones on the right. And so if we want to make this a little more useful, we could say, okay, I actually want to see them by region, not by zone. So let's group the zones together. So we're going to sum them together, but in buckets, saying all the zones matching EU West together, all the ones matching US East together, and so on. And we're going to group by state in this example. So now we get a graph for all the active jobs, and then we know that we're going to get a graph for failed jobs or something like that. And what it's showing on the graph is just how that compares for the different zones, or regions actually, because we sum the zones together. As you can see, there's also like Vimeo DF and Vimeo LV. Those are the upper two. That's just because our data centers don't have multiple zones. But all the Amazon ones are summed together. And you can just completely flip how you display this information by just saying group by zone. And that basically gives us a graph for every zone, and on the graph you compare the different states. And then I have another example. Let's say I want to see the megabits per second of network for all servers matching a certain regular expression and summed by server. So that gives me the network throughput summed across different servers of our network. And one thing I didn't mention yet is that when you click on the legend entries, you can actually inspect which metrics are being included in that time series. So in this case, it displays a bunch of metrics that are being included. And you can see that the unit tag is actually set to bytes per second. And even though we queried for megabits per second, and Graphite actually sees which units are compatible, so it automatically converts the data to represent it the way we want to see it. Another example is using the same metrics. Let's say we want to query it by saying unit equals terabytes. So now it's actually going to integrate the data automatically for us, and it's going to show the cumulative total over time. Then the other example that I actually use often is if you have a unit with, if you have metrics with a unit in bytes, because it's like a gauge of disk space, but you query it for gigabytes per day, then it's actually automatically going to derive the data. And like this, I can see the rate of change on a graph per mount point, how all my different servers gain or lose free space. Okay, so those are all the main features I wanted to talk about. I actually have a few bonus ones too. The graphs are interactive, so you can inspect data points, you can zoom. You can also set alerts, which can be convenient. For example, in this case, and you can set alerts on both Graphite expressions and on queries. So in this case, I have a very simple query that shows me a graph of every server and then shows me the free space on every mount point. And it's going to apply the thresholds and do the alerting for every single mount point. But if I would just add sum by server, comma, mount points, it would aggregate everything together, and that way I could easily set alerts on disk space of my entire cluster. When the alert fires, you get an email with a graph, not too fancy. Also, there's integration with events that are stored in Elasticsearch. And for this, I typically use Anthracite, which is an application that manages events in Elasticsearch. It has flexible schema, and it has a few interesting features like integration with GitHub and stuff. And so whenever you see an anomaly on a graph, but there's no event for it, you can click on the graph and add the event to Anthracite. Or the other way around, if you're looking at a graph, you actually have full text search. So I don't know if you can see, but in the query input all the way on the right, it says statsd. Well, that's just me querying for statsd, and then it shows me all the events that have something about statsd. And that's just displaying what happened over there. It also has dashboards support, and dashboards are very simply just a list of queries, and every query has one or more graphs. But the cool thing about this is that there's a little text field on top, and whatever you type in there gets applied to every single query. So you can use this to drill down into specific servers or to do some kind of averaging And what I like the most about this is that the dashboard definition for this is like very conceptual and high level. Hey, I want to see my CPU usage summed by core and stuff like that. It's not dependent on any particular agent or something like that. Another thing that can be useful is how it colors. So for example, you just specify once, hey, I typically want to see my idle CPU in green and my user space CPU in blue, for example. So if you're composing a graph that shows for every server all the CPU states, it's going to honor those colors for you. But if you would do group by CPU state so that you would get a graph of, say, idle, and then comparing all the servers, it wouldn't apply the same color again, because then everything would be green. So it knows when and when not to apply the coloring. I also have a few ideas for future work. And think about this. Storage aggregation rules, like what Graphite has, and those Graphite API functions, and graph renderers, what do they have in common? Well, the thing that all of those do is they take a sequence of data points, a sequential bunch of data points, and then merge them into one data point. For the storage aggregation rules, that's because you want to move data from high resolution to low resolution. The second one is like on request if you just want to display it a certain way. And the third one is for graph renderers. But for the first two, you always have to explicitly configure those functions. And for the latter, for the third one, usually, the graph renderer, if it has more data points than pixels, it's going to merge those data points together, usually using an average function. And there's a lot of room for mistakes here. I've seen a lot of people corrupting their data or just displaying their data incorrectly. So my thinking is, well, if we have metrics that are self-describing and standardized, then we don't need to do any of this anymore. That you can just say, hey, stat is upper or lower or something like that, or my target type, I'm a counter. And so all those things, the storage aggregation, the graph renders, they automatically know what is the best way to render or to aggregate this data without any explicit configuration. And a graph renderer could even do a few more interesting things, like if it sees that there's several versions of a metric available with different stat fields, it could say, which one do you want to see? Do you want to see the upper values, the lowers, the mean? Or it could even display multiple of them and just display them as a range, maybe with the mean in between or something like that. Also, right now, when you enter queries into Graph Explorer, you often have to know what you're looking for in advance. I'm not an Elasticsearch expert, but it would be cool if someone who knows what he was doing would add some kind of suggestion mechanism to Graph Explorer to automatically suggest new patterns that you could add to your query. And then finally, I think this is my last one. Imagine all the metrics across your entire stack, if they encounter any kind of errors, they would all submit them using a unit tag that is like standardized to use the error unit. The things that allow is you can build user interfaces that see errors, and you could drill down in them and then see how different dimensions or different tag keys and values compare in their error counts, and that way you can narrow down. Or for anomaly detection, for those people working on that, you could do interesting things like figuring out, okay, error counts across which dimensions differ, or which tag values have a lot more error counts than other ones. Or maybe you have errors happening here and then errors somewhere else, and you could deduce that by looking at the tags. So in conclusion, I would say that having metrics that are structured and self-describing and standardized enable a lot of useful things. And in particular, I think composing graphs should be a last resort and not a default, because you can go a long way with just queries. And finally, if you think this sucks or is a bad idea, please tell me why, because I want to learn more about this kind of stuff. If you have any input, let me know. If you think this is neat, please help me make it better. Maybe you want to adopt the native 2.0 format, or maybe you want to extend the structured metrics library to recognize more metrics in the wild. And that's it. There's some URLs that you might find interesting. Let's see. I think we have a few minutes for questions.
Yeah.
Yeah. So the question is, there's a format from OpenStack. Have I looked into it? I actually haven't heard of it yet. When I looked into it, I couldn't find anything like this. And specifically, the metrics coming from OpenStack Swift, I saw a bunch of them in just statsd format. But I definitely want to check that out now. Thanks.
Yeah, it's a DMTF standard, DADF.
Thanks. Yeah.
What kind of throughput for metric updates have you been able to do with Carbon Tagger?
When I tested it, oh yeah, sorry. So what kind of throughput have I been able to get with Carbon Tagger? And when I tested it, maybe I wasn't testing it properly, but it was high enough. Like I don't remember the exact numbers. Either way, it's not holding us back. At Vimeo, we have 370,000 metrics, and each of those comes in at once a minute, and it's holding up really well. But I haven't pushed it far enough yet. It's in Go, by the way. StatsDemon and Carbon Tagger are both in Go. All right, I think that's it. Thank you.